turmoil, but last couple of months I've been working from home, and I think I lost my ability to use public transport. Today I'm going to talk about like a tiny project that we have with Dylan McDermott and Tarmo Ussel from Reykjavik and Tallinn. So it started as like a problem in the usual semantics of programming languages, but we quickly realized it is something that can also be looked at from a more combinatorial, so to speak, way. And so we thought that this workshop might be the best place to show it to people. And if you at some point realize there's something that is well known, just maybe known in a different language, then that's possible. Let us know. The general area of this is kind of combinatorial approach to category theory and monads in particular. So if you're not a category theory person, don't worry. I will give you all the necessary definitions soon. We want to talk about monads. What monads are possible? So there is an infamous definition of a monad, that a monad is a monoid in the category of endofactors. And the general question, I will not be addressing like this question in its whole generality here, but the general question we are interested in is, we are given an endofactor. What kind of monoid structures are there? What kind of monoid structures we can define for a given endofactor? And this is not only like a silly exercise, because things like this appear when we think about compositions of monads. So this is like a known problem in semantics programming languages. We have two.
Give me 1 second. We forgot to share the screen. So
okay. This is the first slide anyway. So
okay.
Okay. When the problem is given two monads that represent, say, two different computational effects or things like that, can we compose them? And in what way? Can we define some form of this monoid structure? Okay, so but in this talk, I will focus particularly on one endofactor. It is endofactor of lists on the category of set. So the category of sets and functions. And by list, I mean like finite sequences of some values. So this is a very much work in progress. There are some known results. There are some new results that I will show you here, and I will discuss some directions where we can take it from here, right? And the main technical result of this talk, I will tell you how many list monads there are, how many monads on lists you can define, but I will not reveal it yet. Okay, so first some notation. So my notation will come mostly from like programming languages and category theory. So I will write LA for like the set of all lists with elements coming from the set A, and I will just define a list by enumerating the elements in square brackets. Then I will use this plus symbol for concatenating lists. So 1 to concatenate 3, 4, 5 is list 1, 2, 3, 4, 5. So this comes from Haskell, and naming conventions that also comes from Haskell. Is I will use X, S, Y, S, and so on for lists of some elements. So I fix some set A, and then when I say XS, I mean the set of lists of elements from A. XSS is a set of lists of elements coming from A, and XSS is a set of lists of lists coming from elements coming from set A. And one super important operation is so-called map, which I denote as LF. So I have some function f from A to B and a list of elements from A, and then LF is applying this f to every element of the list. So it is in programming is often called a map, as a function map. In categorical terms, it is like this functorial action. This makes lists a functor that exists there exists this map function. Okay. So with this, we can define what a monad is. What is this monoid in the category of endofactors? So a monad on lists consists of two families of functions, and these families are indexed by sets. So for every set A, we have this eta, which I will call unit, which is a function from A to LA. So we transform one element to a list of elements, and this mu, which I will call multiplication, which goes from list of lists of elements into a list of elements. And these two have to satisfy some properties. And there are five laws, which at first might seem complicated, but I hope I will be able to explain this to you quickly. So this unit and multiplication need to behave kind of like a monoid. So if you look at the types of these functions, you will quickly see that there are two ways to go from lists of elements to a list of elements. That is, you have like a list of lists, and then you can either first use this mu on the inner lists, and then you end up with a list of lists, and then you just use this multiplication. Or you can first use this mu on the outer level, and then use it again in the result. So you either first kind of squash these two layers or these two layers. So that's how mu works. And then unit needs to be like unit of this multiplication. So when you start with a list, you can use this unit to produce a list of lists, treating this LA as this type of for this eta, and then you just use mu to go back to LA, and then you should end where you started. And the same thing when you apply this eta to every element on the list, and then use mu, you go back where you started. I will give you an example, of course, in a moment. And there are two more laws, which kind of says that you cannot look at the particular values of the elements. This is called naturality. That is eta and mu need to work in a similar fashion for every set A. Never mind the details of this now. I will get back to it in a moment. So an example. So when you Google keyword list monad, what you will see is this thing is usually referred to as the list monad. It is commonly used in functional programming to model kind of non-deterministic computations with multiple outputs, right? And it is quite simple. So this eta for every set, I forgot these indices, but as I said, they are not that important because mu and eta should work kind of the same way for every set. So eta just takes an element and creates a one element list. And then for this multiplication, what you do is just take every list and concatenate it. So for example, let's look at this, right? You have mu of a list of lists here. Lists are 1, 2, 3, empty, 4, and 5, 6. And then mu just concatenates everything, so you get the list 1, 2, 3, 4, 5, 6. And this mu law that says that things should be associated, that mu should be associated. Well, in this example, it looks like this. Like we have a list of lists of elements. So we can either just concatenate the outer lists. So we treat this inner lists as elements. So here we have like a 2-element list, and here we have a 3-element list, and we just concatenate everything. Here we get like a 5-element list, like this, and this. And then when we concatenate again, we get 1, 2, 3, 4, 5, 6. But we can also first concatenate the inner lists. So this one and this one, and we are still like working with a 2-element list. There is a missing bracket here. But then when we concatenate those, we go back to, not go back, but we get the same result. So this is what monad is in this particular case when we focus our attention to sets and functions and lists. Okay. I said that we are working with 2 families indexed by sets, but we have these 2 natural laws. So if we think carefully about this, that gives us that actually it is enough to define this unit and multiplication on the set of natural numbers. So if that works, you can be sure that it will work for any other set using this fmap thing or map thing and so on. So the intuition is that you cannot look at what the particular element of the list is. You just look at the shape of the list and proceed based on that. All right. So so the question that we ask ourselves is, are there any other monads on the list functor? So so these are the results from our PPDP paper from 3 years ago now. So one example is what we call a global error monad. So it works in a similar fashion that the unit is still a singleton. But if one of these lists is empty, we do not concatenate, but we just say, oh, this is empty. Like, so we kind of treat empty list as an error. And well, if there is an error in any of our outputs, then the entire computation just fails. And if there is every list has at least one element, we just concatenate. There is no error. There are more complicated monads. Oh, this one is actually simpler. It is kind of the smallest, in some sense, the smallest possible monad, because we have the eta, that is again a singleton. Then we have these 2 rules for a singleton and for a list that consists of singletons. So they kind of have to be like this because of the unit laws, right? So we have to have these 2 rules if we have this kind of eta, but then everything else goes to empty list, and that's also a monad. And they're also quite.
So excuse me, is this one called mini because it's somehow the lowest possible?
Yes. That's so the name comes from the exotic list monads library that we implemented based on this paper. So we had to come up with a name for every monad. So this one, for example, is called maze walk for a reason. I don't know if I will have enough time to explain why, but what I would say is that some monads are more complicated. So we define this function p that turns a list into a palindrome by just taking the first elements, the initial segment of a list, reversing it and concatenating it. So from x1 to xm, we go to x1, xm, and then back to x1. And then we, instead of concatenating things, we concatenate lists, but first we apply this p to every list except the last one, and this also gives us a monad.
How did you verify the equation for these monads?
This one, for example, comes from a equational theory. So it is. This one is easy. This one is complicated. I only left it in Haskell because it would just be it's almost an algorithm how to calculate this. And so we didn't verify this by hand because this monad and the previous one, they come from an equational theory. So you can just start with a binary operation, a nullary operation, write down some equations, and then if the normal form of that give you a list, then you know you have a monad. So that's like kind of like a more technical trick from category theory / abstract algebra. This is some very complicated monads. You check if there's a singleton in the initial segment of the list, or the last element is empty, and then you do some crazy thing. You replicate the last element n+1 times. You additionally take some only singletons and so on. So there are some very complicated list monads. So to sum up this, what we know from before, the results published some time ago, we know that there are infinitely many list monads, because when you look at this example, it is all parameterized by a natural number n. So for any natural number n, you get a different monad from this construction. And that they can have rather complicated definitions. So it is not that they all have some very simple forms. They can be very complicated. So it's often not that easy to think about how they work. We know that there are monads that can discard, duplicate, and shuffle elements of this list. We know that there are infinitely many list monads that arise from finite equational theories. By finite, I mean a finite number of operations, finite number of equations. But there are some list monads that do not arise from any finite equational theory. I guess the mini monad is one example. We know that there are infinitely many monads, but how many exactly? That is our question. So what we know, that there is at least Aleph-0 list monads, so at least as many as natural numbers. But we also know that every list monad can be characterized by this multiplication and unit for the set of natural numbers. So to define a monad, we actually need this function and this function, and there are only like continuum many functions of this type. So we know that it is, well, either this or some continuum hypothesis. What I want to show you now is, well, kind of like step by step how we got to our result. So I will show you also one failed attempt in order to maybe build some intuition. So if you look at this and this, then the first thing you try is, well, is it just possible to construct this many monads? So if you construct this uncountable set of list monads, then we're done. We know there are exactly continuum many list monads. What we looked at is something I called core list monads, where core stands for concatenate or error, by which I mean this global error. That is for every list monad from this point on, I will say that my unit is singleton, and when I have this multiplication, the result is either empty or equal to the concatenation of everything. That simplifies things, because I can define a monad by just saying, I like specifying the sets of lists for which we concatenate, and everything else is empty. So that, because like a monad is like an infinite object. I want a way to talk about them, to talk about this infinite object. So I just focus on monads of this shape, which will give me like a tool to talk about this. So our first attempt, for want of a better name, I call it a good sets attempt. The idea is, well, you have like in this associativity law, you have like a list of lists of lists, and then you either concatenate on this layer or on this layer. So the thinking was, take like a property that is in an appropriate sense preserved by this concatenation, so that if we concatenate the inner layer, we will be left with things within this good set, and if we first concatenate the good things on the inner layer, we will produce a good set. So, the definition says that a set is good if set C, that is a subset of natural numbers, is good if 0 is not in C, 1 is in C, and it has this strange closure property that we have a number of elements in C, and their sum is also in C, but like the number of these numbers, this K, also needs to be in C. Right? And this is something that gives you if you try to prove that the associativity law holds, exactly what you need, because this kind of says, well, when you concatenate, you just don't jump out of this good set. So you're good to go. And examples of good sets is like singleton one, this set of all odd numbers, because the sum of odd number of odd numbers is odd. And for example, we start with 1, sum n, and then all numbers greater than n, because of course we will, we cannot just add this one fewer times than n times. So we will be back here. So okay, that's pretty cool. So how many good sets are there then? And it turns out that of course, I should tell you what the monad is. The monad is that the first two laws are needed for the unit law, so you will see them every time. And then you just say, well, if you multiply like a list of lists where every list is of the kind of good length, by this I mean the length of the list, and also the number of the lists is also good, then we concatenate, and everything else goes to the empty list. So in this language of core list monads, we say that, well, the set of lists that define this monad is a list of of good lengths, right? So we have a list of lists, and it has to be of good length, and every inner list also needs to be of good length. Okay, so if we can show that there are uncountably many good sets, because this is some subset of natural numbers, so there is a chance, then we might construct an uncountable family of list monads. But sadly, it's not so. And the proof is quite simple, because if we just take any good set and move it by 1, so we just subtract 1 from every element of this good set, it turns out that we are left with a numerical monoid, that is something that 0 is in it, and for any 2 elements in C minus, they are also in C minus. So just a set with closed under addition. And it is known that there are only countably many such sets. This is like an exercise given to students often during computational complexity exams, where it is formulated as like a clean closure of any set over unary alphabet is regular. That's the same result. Okay, so the second attempt. Well, this one was successful. Sorry for just pulling the rabbit out of the hat. But the lesson from this good set is that there is some form of I don't know how to call it, density here. Like because you have something, and then suddenly you have to have this sum of these things, because this associativity law demands it. So the idea is that we are looking for something that is more sparse. That is, when we multiply something, we end up with something that actually doesn't take part in anything. So this is how it goes. We have a subset of the set of odd natural numbers. It's called G, like any subset of the set of natural numbers, and we define the monad like this. So this unit is singleton, and of course the first two rules need to be there because of the unit. And then we say, well, we kind of accept, so we don't go to empty list, we accept only list of this shape. So it needs to have two elements. Second element need to be a singleton. The first element need to be a list of length in G. Right, so intuitively, the proof is a bit more complicated, but intuitively, we end up with a list of an even length. So whatever happens, this list will not kind of satisfy this, and it will not interact with anything else. If we have something like this, let's say in the inner layer, we go to this, then everything will go to empty list for sure, because whenever we want to do something with this, when we try to multiply the outer layer, well, this is of even length, so there is no rule for this. More or less, like that's the intuition. So so here you go. This is a construction of uncountably many list monads, because there are obviously uncountably many subsets of the set of odd natural numbers. But the most important part that I wanted to talk to you about is what about it? Like what to do with this, and if I believe that there is something more to be discovered here. So we now know that.
Just a question again. How do you know that that's a monad? How did you?
No, this requires just a proper proof. Okay. There's a proof in the abstract. Okay. So it's like 2 pages of case analysis. It's like usually like very monotonous case analysis here, because the mu is defined by like 4 cases, and we have a list of lists. So just imagine a lot of case analysis. Yeah. So we know the cardinality of the set of list monads, but that's not entirely satisfactory, because what we would like to have is some form of, if it's possible, a classification, characterization of list monads, or maybe core list monads only, because this is something about lists of lists, but we don't look at the elements. So actually it is about like lists of natural numbers, which stand for the lengths of the inner list. So can we formulate this property that like a set of lists of natural numbers give a core monad or not? And so that's one open question, whether there is some theorem, or maybe being a list monad is a very random property, just some things are, some things aren't, without like any nicer characterization. We have some hypotheses. For example, we believe there is no list monad with this unit different than a singleton. We do that by trying to like generate like partial definitions of mu using like an exhaustive search. Well, not that exhaustive, because these are partial definitions. And well, and then we try to look at counterexamples. But so far, it seems that these counterexamples are also very random, and it's not that we can say, oh, look, all these counterexamples have this property, so we can just abstract this out and prove that there is no such a list monad. Again, not sure if it is just some form of random property, or is there a way to do it? Just don't know. So my personal experience is that it's difficult for 2 reasons. One, because every list monad is an infinite object, so it's not that we can like list all the monads or candidates for monads. That makes it a bit harder to work with. And and my problem is that working with lists has high mental complexity, by which I mean just too many lists on too many levels, and trying to somehow bring this complexity down is like the desired solution. So all our results are quite elementary, in the sense that we didn't use any advanced techniques, and it'd be super nice to have something like saying, oh, but these monads just correspond to this kind of crazy algebras for which we know some combinatorial properties and so on. But at the moment, we have no idea what could that be. And the last slide is, well, there are also other factors that we can look at. So, for example, the non-empty lists. We can define different monads on non-empty lists. And in the previous paper, we show that, well, we can just take any list monad and transform it into a monad on non-empty lists by taking like identity times list construction. Like it is known that like a product of two monads is also a product. So we take like a monad of one element, always one element, and possibly empty lists that give us exactly non-empty lists. This means that we also have uncountably many monads on non-empty lists. And this construction seems to extend to monads on multisets. Just if you look at the proof doesn't say anything about the order of elements of these lists. So not 100% sure yet, but it seems that it also gives us a continuum of monads on multisets. And there are also some I would say strange results that I don't know what to think of. That so we can transform every list monad into a monad on non-empty lists, but just adding one element. But we could also try like the other direction. We start with a non-empty list monad, and we try to come up with a list monad by saying, well, we freely adjoin global error. That means whenever there is an empty list anywhere, we go to empty list. If there is no empty list, we just use the mu for the non-empty list monad. And this sometimes it gives us a monad on lists, but sometimes it doesn't. And it seems that it works exactly for the list this non-empty list monads that do not discard elements. They can shuffle the elements, duplicate them, but if they discard, at least one rule discards at least one element, and this just doesn't work. So this is quite amazing, because if it's true, I have absolutely no idea how to prove that this is always the case. And so as you can see, I think there is a lot of conjectures here, a lot of interesting things that we could still research. So we are very open to any comments or suggestions if this rings any bell or has any connection with anything that you know of. Okay, thank you.
Yeah, thank you very much for this talk. Are there any questions? Yes, please.
So things seem to be nicer for monads which do not discard elements.
Yes.
Are other things nicer for monads which do not discard elements?
I don't think so. So there's one more construction that is interesting. So just a moment. So if I have time. So there is one monad that I think is a monad. I still don't have a proof, but it is monad like these two rules, of course, hold, and then you have one selected list of lists, and here you can write any affine combination of the elements. So you cannot discard, but you can duplicate, shuffle, whatever you want, and everything else goes to empty. And this also seems to be a monad by checking. I do quick checking and so on. So this is also important if you do not discard element, because if you discard at least one, it is not a monad for sure. So maybe there is something deeper to this non-discarding, but can't tell you anything more except for that. Yeah.
You continue your question or you? No, another one. Then Martin.
Thanks, that was amazingly fun.
Thanks.
Have you considered simpler functors? Is it this naive questions, but can you do similar thing, I don't know, for options, for instance, or something real? Is it too simple in the
I didn't put it here, but I believe we know the number of monads on the PowerShell factor, and that is 2. There are 2 monads on the PowerShell factor, I think. And the simpler ones that always have the like a fixed number of elements, or at least some bound, like maybe like pair. It's quite easy to come up with all the monads, because it is, you have very limited options. You just check all of them, and that's it.
Then you have an example where this is not finite but countable?
No. That's
Yeah.
So I had another question. So the other way, the other question is also seems interesting if you have a linearity hypothesis that every element is used at most once in your school. It doesn't add something interesting.
don't. No. I think we didn't see anything interesting.
Okay.
Interesting with that.
Thank you.
Yes, of course, it is possible to do that, and I think it should be a bit easier. But for no other reason than where we got enough work with this. This usually requires like a lot of computer searches and so on to get any intuition. Also not, but also for the same reason.
Okay. So then let's thank the speaker again.
Thank you.
And we start with the, well, after the settling the technical issues, we start with the last talk of the